Hi folks, we're going to take up the rest of the derivatives on this lesson. All right, so here now we're going to work with y equals x cubed. And we do know what y equals x cubed looks like. Looks something like this here. So one thing I notice is that all the tangents seem to have a positive slope, except maybe at 0. It kind of looks like the slope at 0 might be horizontal. Well, we'll see. But definitely for most of the values, we are going to end up with a positive slope. So it'll be interesting to see what happens when we find the function, the derivative function, that produces the slopes of the tangents for any x value. Okay, so we start again with that limit definition of the derivative. Okay, f at x plus h minus f at x all over h. And now let's input this into our function. Okay, so here I'm going to replace x by x plus h. So x plus h all cubed minus x cubed all over h. Okay, and this here is going to require a little more work than the previous one because I'm going to have to, first square x plus h. Okay, so I'm not going to write that out. I think I can do that without writing it out. So x plus h squared. In fact, we have it right next to us. Okay, so we have an x plus h that's left over, and then times x plus h squared. So that's just going to be x squared plus 2hx plus h squared. Okay, and then minus x cubed all over h. And now this is where we're going to try to be very, very careful here as we're expanding this. Okay, so we have x times x squared. There's going to be x cubed. That's our only cube term. Okay, let's maybe take our time here just to make sure we don't make any mistakes. So here x times 2hx is going to be plus 2hx squared. Okay, x times h squared is plus xh squared. All right, now let's do these here. There's another hx squared. Okay, here's a 2h squared x for that one, plus 2h squared x. And then finally, h times h squared is h cubed. And then, of course, the minus x cubed all over h. All right, so let's see if we can simplify this here. And the first thing I notice, which I don't think I should be too surprised about, is the x cubes cancel out. All right, so here I have an hx squared, and I've got another hx squared. So 2 plus 1 is 3hx squared. Okay, we also have an xh squared, okay, and 2xh squared, add them together, plus 3xh squared, and then finally h cubed. And this is looking all very promising because now I can factor out an h from that numerator. Okay, so let's factor out the h, and what are we left with? Well, we're left with 3x squared plus 3x, there's still an h there, and plus h squared, and then all over h, and lo and behold, there we go. The h's cancel out, and now I can evaluate this derivative. Sorry, this limit. Okay, now, similar to what we talked about before, 3x squared is not affected by h approaching 0. Regardless of whether x is 1 or 2 or 7 or 112, this expression is just going to remain 3x squared. Let's look at this one here. I've got 3x, which is unaffected by h approaching 0, but it's being multiplied by h. So as this approaches 0, this whole term is going to disappear. And of course, h squared, again, as h gets closer and closer to 0, this whole term is just going to disappear. And look what I'm left with, just 3x squared. Okay, so again, what does this represent? This is the function whose outputs are the slopes of the tangents. And remember what we talked about earlier? We noticed that most of these tangent lines are going to have positive slopes. And of course, 3x squared is positive, well, almost everywhere. The only place this is not positive is at x equals 0, where the whole thing is equal to 0. And we look at our graph at y equals x cubed, it doesn't seem outrageous to think that the slope of the tangent there might be 0, because it looks like the tangent might be horizontal. So again, we've now gained a whole bunch more power, because by finding the derivative function, I don't have to go through this process every time. I seem to only have to go through it once, and then I can calculate any derivative I want. Okay, any slope of tangent that I want. Okay, so if you haven't finished the next one, take a pause, do it, and come back. Otherwise, we'll take up the next one. So notice before we worked with functions, power functions, where the exponents were integers. Let's work with a power function where the exponent is not an integer. Okay, so let's do this here. So we got limit as h approaches 0 of f at x plus h minus f at x, okay, all over h. And so here I'm just going to input x plus h. So x plus h to the 3 over 2 minus x to the 3 over 2 all over h. Now this is where things get dicey. Before, I was able to just, distribute this because I had an integer exponent. So I could do x plus h squared or x plus h cubed. Here my exponent is not a positive integer. But what I hope you noticed was that when you have an exponent, which is a fraction over 2, the 1/2 portion of that fraction just represents a square root. Okay? And since I have these values stuck inside a square root, I don't think you're going to be too shocked to find that I'm just going to multiply this by the conjugate plus x to the 3/2. Okay, and of course, if I do it to the numerator, I have to do the same thing to the denominator, plus x to the 3/2. And let's see if this is going to work out. So notice I didn't write as a square root, but I know that over 2 represents square root. So this is going to produce a difference of squares. The middle terms cancel out, of course. So what happens when I do x plus h to the 3/2 times x plus h to the 3/2, where the bases are the same? So I could just add the exponents. So 3 over 2 plus 3 over 2 is just 3. So I'm left with x plus h cubed. Okay? And then here minus, again, x to the 3 over 2 times x to the 3 over 2. I can just add the exponents. This is just going to be minus x cubed. All right? All over this thing, well, not the nicest thing in the world, but we'll write it out. X plus h to the 3/2 plus x to the 3/2. Okay? And at least now I can do some algebra. Now, I'm not going to re-multiply this out because I happen to have done it in the previous example. We already determined the expansion of x plus h cubed, so there's no point in doing it again. So I'm just going to write it out, and I'm also going to sort of write out the simplification. So this ended up being x cubed plus 3x squared h plus 3xh squared plus h cubed. If you look back and do some simplification, you'll see that that works. And then, of course, the minus x cubed all over h times this thing. I have to say, I'm very happy that we're able to determine this method for not having to do the limit definition every time we need a rate of change. But I gotta say, this also seems to be a lot of work. Does this mean I have to do this for every single function? So I shouldn't complain. We just figured out something that's going to save us a lot of time, but boy, it'd be nice to save some more time. Well, who knows? We'll see. All right, so there we go. As before, can factor out an h. What are we left with? 3x squared plus 3xh plus h squared. And lo and behold, as before, the h's cancel out. And now we can determine what happens as h approaches 0. So this just remains 3x squared. This is going to disappear because I'm multiplying by something approaching 0. This is going to disappear because the whole thing is approaching 0. And let's take a look at the denominator here. This is going to become x to the 3 halves because h is getting close to 0, plus another x to the 3 halves. And so what I'm going to have is 2 times x to the 3 halves. Oops, 3 halves. But this is where I realize I can actually simplify that a little more because I've got a division of 2 powers of x. So I've got my 3 over 2. But what is this going to be? What is 3 minus uh, 3 over 2? Okay. Oh, sorry, this is, I just realized, 3x squared. Whoops, almost made a very serious error there. This was 3x squared, not 3x cubed. So sorry, I have to do 2 minus 3 over 2, which is 2 minus 1.5, which is just 1/2, or 0.5. And again, a fairly nice expression. I don't think I should be too surprised that it's a little more complex than the previous ones we found, given that the original function was a little more complex. But, you know, it's almost like I'm seeing something familiar here. It's not coming to me yet, but it feels as though I'm seeing something familiar. Well, let's just leave it for now and see if we can, maybe just go a little further. And so now, to do something a little different, let's work with a function which involves more than one term. So far, everything's involved just one term. Let's just look at more than one term. Okay? So, if you haven't done this one yet, you should pause and come back. Otherwise, we're going to take it up in a second. All right, so let's take the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, so wherever I see an x, input an x plus h, so x plus h squared plus x plus h. Okay, and then all of that minus the function evaluated at x, so x squared plus x. Okay, and this is actually significantly simpler than the last couple we've done. So let me expand that there. X squared plus 2hx plus h squared plus x plus h, and then minus x squared minus x. Don't forget to distribute. Okay, all over h. And one thing I notice is the x squared minus x squared disappear. And look at that. The x minus x disappear. Okay, so as we've seen now many, many times, it seems to all work out. So what are we left with? We're left with 2hx plus h squared plus h. They all contain a factor of h. So I'm going to factor that out. So here we're left with a 2x. Here we're left with an h. And here, if I factor out an h, I'm just left with 1. And of course, this reduces with the h in the denominator. And now I'm able to take the limit. So 2x is not affected by h approaching 0, so it stays the same. This approaches 0, so it's disappearing. And 1 is a constant. It's unaffected by h approaching 0. Okay, and so now we see, as before, we're able to determine a function. Okay, and what does this new function give us? It gives us the rate of change of f for any x value I want without having to do this every single time. Okay? But as I referenced earlier with this more complex example, this means that as soon as I change this to instead of x squared plus x, my function maybe is x squared plus 2x, that means I have to do this process again. And does that mean I have to do the same process for x squared plus 3x and just more complex functions? So this is where, given that we've still got a lot of time in this course, we have to hope that maybe there's even more to this story. And the last thing I want you to do, okay, I want you to think about looking back at all these derivatives we found. Are there any patterns that you can find? Is there more to this story than just this extremely important discovery we made that we can find these functions that give us the rates of change? Can we go even further and get something even nicer? Okay, that's it for now.